Hello and welcome. Today we're going to be doing BMO2 2018 question 2. The question says there are n places set for tea around a circular table and every place has a small cake on a plate. Alice arrives first and sits at the table and eats her cake. Next, the Mad Hatter arrives and tells Alice that she will have a lonely tea party and that she must keep on changing her seat, and each time she must eat the cake in front of her if it has not yet been eaten. In fact, the Mad Hatter is very bossy and tells Alice that for I equals 1 to n minus 1, when she moves for the ith time, she must move ai places, and he hands Alice this list of instructions a1, a2, an minus 1. Alice does not like the cakes and she is free to choose at every stage whether to move clockwise or anti-clockwise. For which values of n can the Mad Hatter force Alice to eat all the cakes? Okay, so we can think of this question as, so let n equals 6. So there will be 6 plates. Okay, and the Mad Hatter wants her to visit each plate at least once. And so he gives her a slip of paper with these instructions. So if he says 1, then Alice can either go to this one or this one, assuming she starts here. But if he says 3, then she can go to this one only. I wasn't really sure how to think of this problem, so I started by just using n equals 1, then 2, then 3, and just going up using small numbers. So when n equals 1, it's very obvious. Alice eats the cake and she immediately loses, where the Mad Hatter wins if Alice eats all of the cakes. Then for 2, all the Mad Hatter has to do is give her a slip which says 1, because she eats this one and then this one. For 3, Alice can always say, so if she starts at the top one, so here, she can always say that she doesn't want to go to this cake. So whatever the Mad Hatter says, and he can only give her 2 instructions, so 1, 1, or 1, 2, she can always choose to not go to this cake. For 4, what you'll notice is that the Mad Hatter can force her onto this plate, then he can force her onto one of these plates and onto the next one, the opposite one. So you can always force someone if n is divisible by 2. You can always force someone onto the opposite plate. So when n is divisible by 2, if you say n over 2, they will always be on a plate that you know. So I carried on for 5, but the same thing happens as 3. She can always choose to not go to this one, no matter what happens, because she can't be forced onto this one by going onto another plate. With 6, she can choose that she doesn't want to be at a position, and then this is still possible because the Mad Hatter can't force her onto this, because the opposite she will never get onto because she's chosen that. Seven is basically the same. She can choose not to go onto this one and there's no opposite. 8, this one's a little bit more complicated, but basically you can figure out that you can force her onto this one and force her onto one of these 2 and then onto the opposite one. Then you can rotate her by 1, then to the opposite one, and then to one of these 2, and then to the opposite one. So really what you're doing here is you can break that down into two versions of the solution to 4. So what you're doing is you're getting Alice onto this one, then to one of these, and basically all of these plates will be gone. Then you can force her onto one of the green ones just by saying 1, and if she chooses this one, for example, she eats that, and then she goes to the opposite one and then does the same 4 pattern. I will then prove that this works for any multiple of 2. So let's start with the solution 2. Here we just go to the opposite one. So here we just go to the opposite one. So what the Mad Hatter gives to Alice is 1. For the solution to 4, we go to the opposite one. Then we shift 1 to the 2. Then we shift 1. Then we go to the opposite again. For 8, we basically do 4, but we times it by 2. So it'll be 4, 2, and then 4. So we times each number in the list by 2. Then we shift by 1 onto the next one, and then we times each number by 2. And so here we start to see a pattern. So for 16, okay, so for 16, we basically do 8, but we times it by 2, so this would mean these bigger ones are all gone. But then we shift 1 and we get rid of all of these. And so from this we can see that every power of 2 is possible. I will now prove why the Mad Hatter fails if n is not a power of 2. Let's name each position going clockwise, 12 for example, and let's say she starts on 1. If we call this greatest odd divisor x, so for 12 it would be 3, and we have to avoid the positions which are multiples of this, so that would be 3, 6, 9 and 12. It's quite obvious why we have to do this, is because if you land on 3, you can be forced onto 9, which means you can be forced onto 6 or 12, and when you are forced onto one of these, you force onto the opposite one. It is possible to avoid these points because no matter where she is, if she's on 1, 2, 4, 5, 7, 8, 10 or 11, she can't be forced onto one of these plates. So for 11, she can only be forced onto 5, but she can't be forced onto anything else. So she always has the choice to go onto a different plate that is not one of the ones that she's selected. I'll do this again with a larger number so you can see roughly how it generalizes. Okay, so I've written the numbers where n equals 24. So the largest odd divisor of 24, well, 24 equals 2 squared times 3. 2 cubed times 3. So it's 3. And so we have to avoid 6, 9, 12, 15, 18, 21 and 24. Notice that there are 8 plates because this is 8 times 3. Again, she can always avoid these plates because she can never be forced onto them, and she always has a choice to go onto a different plate. And so the Mad Hatter can only force Alice to eat every cake if n is a power of 2.